Let's talk about that pulley lab that we did a while ago. So, it's been a while, I don't even remember when it was, but when we talk about work, it's force over some distance, and that force has to be parallel to the displacement. I'm sorry, I said distance, I meant displacement. There's a trade-off with pulleys. So when we talk about mechanical advantage, the higher the mechanical advantage, the easier, right, the less force we had to apply. So what was the trade-off though? We had to do what? More rope, right? So if we just use this very not perfect work equation, because there should be plus or minus and all that stuff. But if we just simply talk about force and displacement, what we got when we increased the mechanical advantage is this force went down, but as a trade-off, our amount of rope increased. And they were proportional. They should be in the basket. I emptied kind of everything out except for the current unit. Third, yeah, that one, right? Yeah?
Yeah.
Okay. So, as our force went down, our rope went up. So, in terms of the amount of work done by a simple machine, it's a wash. The amount of work that a complex pulley configuration makes the same amount of work. If I have to apply 1/5 the force, makes it easier, but my trade-off is 5 times the rope. It's a wash. Same thing with like a lever or a lever. I guess it depends upon how you want to pronounce that simple machine. The idea, if I take a lever or a lever, I don't know what I even use anymore, I switch back and forth so many times. And if I pry on something, in order to lift that thing, you know, if I want to lift like a boulder and I want to lift it only a couple inches, I might have to move that fulcrum or the lever arm feet in order to get that. But the idea is it's that trade-off of force versus displacement. So we talked about a couple different types of works yesterday. And when we talk about the different types of works, there's 4 we're going to talk about today. The work done by normal force, the work done by gravity. I guess that was only 3. Oh, because there's no friction on that one. And then friction. And then we can talk about something referred to as net. And just like net force is the sum of all my forces, net work is the sum of all my work. Now this was a little bit different. When we talked about net force, it was only in the x direction or only in the y direction. When we talk about net work, it's you add them all up and you take a look at them. So there's 4 specific works that we looked at, and each one has its own special formula. And it's all derived from this general equation, work is equal to plus or minus some parallel force times the displacement. And we choose the displacement to be parallel to the force that we're looking for. Okay? Now, we had variations of those, and I wrote those on the board, not on my sheet, so I don't have them anymore. But that's what we're looking at here. So, let's look at the first one. So, Wn stands for the work done by normal force. So what we have, if we look at the object, I have a 10 Newton force applied to push a block across a frictionless surface for a displacement of 5 meters to the right. So my delta x is equals 5 meters to the right. Delta x equals 5 meters to the right. So when I talk about my normal force, it's going to be the work done by my normal force. It's going to be plus or minus my normal force times the displacement. And since my normal force is in the y direction, I'm going to multiply by delta y. Now, we can get into the is it the plus or is it minus discussion on another one, because it really doesn't make too much of an impact on this one, because if my displacement is 5 to the right, what's my delta y equal to? 0, yeah. If it's moving to the right, it's not moving up or it's not moving down. So then when we look at the work done by my normal force, since my delta y is 0, the amount of work done by my normal force is also going to equal 0. And since we're talking about the y direction, I'm going to jump down and I'm going to skip a line and I'm going to look at the work done by gravity. And the work done by gravity is going to be plus or minus, and then we choose the force that we're referencing. We're talking about the work done by gravity. Then we're going to talk about the force of gravity. So this is going to be plus or minus the force of gravity times the displacement. And again, for gravity, I want to choose the displacement that's parallel to the force. So since my force of gravity is in the y direction, this is also going to be times delta y. For the same reason we just said in the previous one, the amount of work done by gravity is 0. So because the delta y is equal to 0, the two forces that are acting in the y direction also are going to equal 0. Okay? Now, work in. Our work in is going to be plus or minus. Our work in is the work that we use when we talk about our applied force. So it's plus or minus the applied force times the displacement. If we look at my picture, my applied force is in the y direction. So if my force is in the y direction, then I want to talk about displacement in the y direction. So it's going to be plus or minus the applied force times delta x. That's our general equation that we're going to use for applied force.
Wait,
Now,
is it X or Y?
It's an x, because the applied force is in the x direction. So we choose the displacement that's parallel to the force. So because the applied is in the x, we use delta x. We use delta y for normal because that's in the y direction. We use delta y for gravity because that is in the y direction. So we choose the displacement that's parallel to the force, the direction of the force. Okay, so now when we go through and that's our equation. If we go through and we substitute some numbers in, so I'm just going to kind of draw an arrow and say, hey, now let's go and say, hey, well, our work in is equal to, and instead of saying plus or minus, let's make that choice. Is it the plus or is it the minus? Now, to remind you, it's a plus. Work is positive when the force is in the same direction as the displacement. It's negative when they're in opposite directions. And it's 0 if the displacement is not parallel to the force. So when we talk about applied force is to the right, we talk about displacement that's to the right. Are we adding energy or are we removing energy to the system? Is it positive? I'm sorry, I should have said, is it positive or negative work? Positive. That means, positive work means we're adding energy to the system. A negative work would indicate we're removing energy from the system. So since I'm adding, because they're in the same direction, it's going to be plus, then I can take my applied force value of 10, and I multiply by my displacement in the x direction, which is 5, and I get a total of 50 joules, and that's going to be a positive 50 joules. Now when we discuss net work, what that's really just saying is I'm going to take my Wn, I'm going to add it to my W in, I'm going to add that to my WG. I'm simply going to take this number plus this number plus this number. And since this number is 0, and this number is 0, the net work on the system is 50 joules. All that's saying is overall I'm going to add 50 joules of energy to this system. When we talk about a system, we're talking about like an object. Okay, so there's 4 different types of work. We add them all up to get network. We'll do one more together. And I'll give you a chance to do a couple, and then we'll kind of come back to the next one. Okay, so we'll do one more together. What's this one? All right, so this one also has 3. This one doesn't have an applied force. Remember that it is possible for an object to be moving without an applied force. So blah, 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 it's moving, delta x is equal to 5 meters to the right. Okay? So 5 meters to the right is my displacement. So work done by my normal force is plus or minus my F of n times the displacement. Is it delta x or delta y for my normal force though? My normal force is in the y direction, so my displacement is going to be also in the y direction. Now what is my delta y? If it's moving 5 meters to the right, my delta y is equal to 0. So my delta y is equal to 0, which means my normal force does no work. It neither adds nor removes energy from the system. If we talk about work done by gravity again, because we're talking about the y direction, that's plus or minus f of g times delta x, which again is equal to 0. So the work done by gravity is equal to 0. And then the work done by friction is always minus the force of friction times delta x. Why is that a negative? Why is it always going to be negative? Friction always opposes motion, so no matter which direction the object is moving, friction is always going to be in the opposite direction. So if you say, well, do I have to remember that? No, you don't have to. You could remember that plus or minus, and you can say, well, it's always going to be the minus. Or you would say, well, it's moving to the right, friction is left, therefore it's the minus. You could. The other thing is, of these 4 works we're talking about, the 2 that I care the most about are work in and work done by friction. And on your equation sheet, the work done by friction, it has the negative next to it. Okay? Because it's always going to be that negative. But it's in the x direction, right? Because friction is in the x. So then this, if we put numbers in, is going to be minus 10 times 5. So this is going to be negative 50 joules worth of energy. Add them all up. Wn plus Wf plus Wg. Wn was 0, Wg was 0, so what we're left with is negative 50 joules. Negative work means that overall we're removing energy from the system. And today we'll start talking about what forms of energy. Not there quite yet. So the 4, just realize that the first one had 3, the second one had 3. The first one had a work in, not a work done by friction. The second one had a work done by friction, not a work in. But I think there's 4 more that I'm going to ask you to do. Now all 4 are there. Work done by normal force, work in, work done by gravity, work done by friction, add this plus this plus this plus this, get an overall answer. Okay? There's that one. Yeah, there's 4 more. Okay? The answers are posted on the very bottom of the back page that you can check your work as you go. Hopefully you can get them and not just, the intent is for you to work through them. I'll give you a couple minutes. I'm not really sure how long this is going to take. If you want to work with someone, I'm okay with that. But this is only probably going to be about a 5-minute kind of work on something would be my guess about that. So we're going to go through, I'll let you go through those, and then we're going to move on with energy. So there's 4 types of work that we generally are going to talk about for this worksheet. Talk about work in, work done by friction, work done by normal force, and work done by gravity. But the 2 that we really care about are the work in and the work done by friction. That's why on your formula sheet, right below our general equation for work is plus or minus, those 2 I specifically have listed out. So this does say plus or minus on your formula sheet. They kind of look like they blended together a little bit. But those are the 2 that we care the most about. Because can gravity do work? The answer is yeah, and I think there was a couple examples that you had positive work done by gravity or negative work done by gravity. But we can get that work done by gravity in a different way. And we can approach it from an energy standpoint. So we're going to kind of make a transition to energy. So this unit kind of has 3 pieces. Work, energy, and there's a little bit about power. Power is really just taking the amount of work, dividing it by the amount of time it takes to do that work, and we have power. So we're going to do energy. We got to talk a little bit about work because that's going to come into using one of the equations. But when we talk about energy, we're going to start with this idea of mechanical energy. So we're going to define a bunch of terms. We're going to talk about a couple of the equations on your formula sheet. So this would be something you might, I would suggest, writing in a notebook somewhere probably. That's just my suggestion. So when we talk about mechanical energy is the sum of potential and kinetic energies. So when we talk about adding energy to the system or removing energy from the system, we're talking about adding mechanical energy or removing mechanical energy from a system. I think I mentioned this yesterday. There are way more forms of energy than mechanical energy. We are only going to talk about mechanical energy in this unit. And when we talk about mechanical, we're talking about potential and kinetics. There's sound energy, there's thermal energy, heat energy, there's light energy, there is thermal energy, I already said thermal, nuclear energy, solar energy, right? There's lots of other forms of energy. We're just talking about mechanical energy. So mechanical energy is a sum of potential energy, potential and kinetic energies. And there's an equation on our formula sheet that talks about ME. So ME simply means mechanical energy. So this is our variable is ME. It's not super original. But the formula listed, and I'll try to keep it the same order, is simply taking our PEG plus our PEE plus our KE. And if we add those 3 energies together, we'll define those 3 in just a moment. Those 3 energies, we get something referred to as mechanical energy. Now PE, again, pretty original, stands for potential energy. KE stands for kinetic energy. If you talk to students in traditional or AP, they don't write it as PEG, they write it as UG, UE, and I think simply K, just so you are aware of that. I don't. I write it as PEG, PEE, and KE. But you talk to someone and they start writing that stuff, just be aware of it. So mechanical energy is the sum of our potential energies and our kinetic energy. So when we say we add energy, energy is being added to the system, we might add gravitational potential energy, elastic potential energy, or kinetic energy. So our three types of energy are P, E, G, which stands for potential, gravitational energy. Sometimes I change the order of that. It says, instead of saying potential gravitational energy, that doesn't say gravitational, that says gravity. Potential gravitational energy. Sometimes they say gravitational potential energy. And when we talk about potential energy, it's like the ability to do work. So potential energy is the ability of gravity to do work. PEG. There's a formula. It's listed on your equation sheet. PEG is equal to M times G times H. And there's what I refer to as a question. There's a question we ask ourselves, and it's really just a yes or no question. And if the answer to that question is yes, that object has PEG. If the answer is no, that object has no potential gravitational energy. So when we look at our formula, there's mass, there's gravitational acceleration, and height. We don't really have to ask ourselves, does that object have mass? Because anything that takes up space is made up of matter, by definition has mass, so the answer is going to be yes. We don't have to talk about gravitational acceleration, because if there is no gravitational acceleration, there is no gravity, and we're not going to deal with those situations. But in the event that you were floating around in like space, then I guess the answer to that would be no. So really the question is there a height? Okay, and if the answer to that question is yes, then PEG is not equal to 0. It has some value, and we'll have to calculate it properly. If the answer to that question is no, then there is no PEG. Now, height is a relative thing. We could say how high off, what is the height of my water bottle? And the answer could be 0, or it could be about a meter. And it depends upon what we're measuring from, right? So, are we measuring from the table? Are we measuring from the floor? Are we measuring from sea level? Then we're like 1,200 some feet. So a lot of times we talk about, we're really talking about, is there a difference in height? Because we're going to end up comparing two locations. So when we talk about like this location and this location, if they start and end at the same height, then we'd say there is no change in height, right? If we define our lowest point to be 0, it seems like a pretty logical idea. And the lowest point is 0, then they're at the lowest point. No change in height, so the answer would be no. But if the object goes up a hill, or goes down a hill, or whatever, then we can get height. So just, I guess, quick, we should define what all these things mean. I think most of these we're pretty good with. This just are units for all forms of energy are going to be measured in joules. All forms of energy are going to be measured in joules. So this is the unit, I should probably clarify. Unit is going to be joules. M is simply mass. And hopefully we remember that that has to be in kilograms. G is our gravitational acceleration. That has to be in meters per second squared. And unless I tell you otherwise, we're on Earth, 9.8 meters per second squared. And this H, that's really the new one, I guess you could call it. And that's height. And we're going to measure that in meters. So PEG, is there a height? If so, we have to multiply the mass of the object by gravitational acceleration times the height, and we get PEG. If the answer to that is no, then we can say, hey, this value right here is going to also be equal to 0. So PEG. PEE, maybe I should be using the same colors. Sure, I'll try to go with the same color. PEE is potential elastic energy. I'll introduce this today. We actually won't use potential elastic energy for a bit. PEE. So PEE stands for potential elastic energy. Potential elastic energy. So when we talk about elastic energy, we're talking about springs. We're talking about springs again. Kind of like Hooke's law. So it's potential elastic energy. So if potential energy is the ability to do work, it's the ability for a spring to do work. And again, I'm putting spring because it doesn't have to be a spring. It could be a bungee cord, it could be an elastic rubber band, it could be a popper. We'll make poppers in this unit. It has its own formula. It's listed on your formula sheet. Oh, I don't think I should show you. Oh, no, it's on the screen. PEE, and all of these are listed right here. So it's still in that same column. So here's my PEG, PEE, KE. Here's our ME equation. So PEE is 1/2 K times X squared. 1/2 K times X squared. Units still going to be joules. My K value is the same K value that we used in Hooke's law. It's spring constant. And our units for spring constant are newtons per meter. Our X, just like in Hooke's law, is my displacement. I guess it's the spring's displacement from equilibrium measured in meters. So those are not new terms. Remember, Hooke's law was F of S is equal to K times delta X. It's the exact same variables. Instead of saying delta X, I just call it X. We got squared. Make sure you take it's 1/2 K X squared. We're going to kind of put a pause on springs just for a little bit. But when we do, we'll just kind of go through the process of, is there a PEE? So the questions, again, that we kind of ask ourselves for the determination is something that we're going to be focusing on. Is there a compressed spring? And I put compressed because realize it could be stretched. Okay, that's why I put it in quotes, because it, I don't know, maybe I'm improperly using quotes just for the record. Okay, but is there a compressed spring? If the answer to that is Yes, there's a compressed spring. That means that x is not equal to 0. If the spring is at its equilibrium point, the x value is 0 because it's at its equilibrium point. So 0 squared will give you 0 times k times 1/2 will give you 0 PEE. So if your spring is not compressed or stretched, then there's no PEE. If there is a compressed or stretched spring, then you have a PEE. Not sure we'll get all the way through this one, but we'll get started. Kinetic KE is our kinetic energy. And kinetic energy is simply what we say is energy of motion. Energy of motion. So our formula on our formula sheet is KE is equal to 1/2 mv squared. Kinetic energy still measured in joules. M is still represented mass, measured in kilograms. V is velocity in meters per second. Make sure we square the velocity. The question is it moving? Does it have a velocity? I don't have to ask if it has mass for the same reason I didn't have to ask for the PEG. Because anything that takes up space and has matter, it has mass. But is it moving? So if that object has a velocity at all, even if it's really, really small, it has kinetic energy. If it's not moving, the velocity is 0. 0 squared times 1/2 times m is going to be 0. So these questions are helpful because if the answer is no, then we can cross off those forms of energy. If the answer is yes, then we must keep them in our equation. Because most of the time I don't say, how much kinetic energy does an object have? I'll ask, how much mechanical energy does an object have? Because I'm not talking just about kinetic, I'm talking about the combination of gravitational and potential elastic and kinetic energy in these types of things. All right, so that's a good stopping point. Hey, I'm in the wrong class period again. 13. I thought it was 06. The bells are ringing off, but still have a little bit of time. All right, perfect. I didn't have to rush through it. So when we talk about these three types of energy, that's where we're going to be going. And I'm not going to say, does this object have kinetic? I'm going to say, how much mechanical energy does an object have that's some height, some speed, some amount of stretch spring? And then the combination of those will give us our answer. With mechanical energy, I tend to do two types of calculations. I do one location mechanical energy problems, and I do two locations. So if I'm talking about one location for an object, and I simply say, how much mechanical energy does an object have at blah, 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 I'm asking you to solve for ME. Okay? How much mechanical energy does my water bottle have? With a velocity of 0 and a height of 1 meter, and a mass of blah, blah, blah. One location, how much mechanical energy? ME equals question. I'm solving for M. If it's a two-location problem, then I start looking at this equation. Work in plus the work done by friction is equal to my change in mechanical energy. So when we talk about a change in mechanical energy, I'm talking about how much mechanical energy does an object have at the final location, final, not so initial, that's what change means. And I'm going to subtract from how much mechanical energy does it start with. So delta ME is going to be ME2 minus ME1. that equation on the bottom expands out really, really long and ends up having 8 different terms in it. So sometimes people refer to it as the long equation, because when it's fully expanded, it gets kind of long. The nice thing about that long equation is most of the time there's a fair amount of values that end up being 0. And if the values are 0, we can do some pretty significant crossing offs. So we start looking, is it a 1 location or 2 location problem? And then from there, we can kind of make some choices about how to approach this. So, tomorrow,